Okay, next we're going to talk about the spontaneous flow of electrons based on reduction potentials in a voltaic cell. Voltaic cell is an apparatus that allows electrons to flow from the anode to the cathode, and it's all dependent upon which one is has the greater potential to undergo reduction. And so it's a spontaneous flow of electrons that can be measured in voltage. It is essentially a battery. So here's the way it works. So you have one electrode that has a metal in as the electrode, and the other electrode also a metal. And when these two metals are in this apparatus, set up in this way, the electrons will spontaneously flow from the zinc to the copper. And we're going to look at why that happens. These are submerged in ionic solutions to allow free flow of ions. This is called a salt bridge. The salt bridge keeps things electrically balanced as the electrons flow so that the circuit doesn't short out. So here's what happens. The zinc has a certain potential to undergo reduction. And it's a value that you look up on a table. You'll find a table in your textbook on page 863. There's also one that you'll find in the appendix to the end of the book. And then I can also look up the copper ion because I want to see which one's going to actually undergo reduction. And the value that I get for the copper ion is a positive 0.34 versus a negative 0.76 for the zinc. So what this tells me is when these two species are in the presence of each other, that the copper has the stronger potential to reduce. These values, these are standard values that are given in a table, and it's their ability to undergo reduction. So clearly zinc has insignificant ability compared to copper. So what we know is that the copper is going to be the one to undergo the reduction. And so this equation is going to remain as is. The zinc, however, is going to go in the opposite direction. So I take the zinc equation and I flip it around. And when I do that, I change the sign of the value, the voltage value for the zinc. So what I can do then is I can look at the two of them combined, the positive 0.34 voltage for the copper to undergo reduction, the positive ability for the zinc to undergo oxidation. So when I turn the equation around, I'm now showing that it's undergoing oxidation. And if it has a low ability to undergo reduction, then it has a high ability to undergo oxidation. And this one I know is in the oxidation format because the electrons are on the product side. This one is in the reduction format because the electrons are on the reactant side. And the table is set up for the reduction. So when I get this value that I calculate here by adding these two cell voltages is 1.10 volts, and that is what we call the electrode potential for the cell. And so here's another example that you could experiment with, which is the reduction potential of nickel versus the reduction potential of iron. And we can see that nickel having the lower negative value is going to be more likely to undergo reduction than the iron would be. So then I can say that this would be, for this one, the E of the entire cell. That's what we call it. The two half reactions are half of the cell, and then the full is going to be, it's going to be equal to the E red of the nickel plus the E ox of the iron. So what does that mean? I'm going to take negative 0.28 for that nickel, and I'm going to add it to the positive 0.44 for the iron, because this one had to get flipped around. So this one I confirmed to undergo reduction. This one, since it's a lower value, higher negative is a lower reduction potential. And so that one's going to undergo oxidation. So I change the sign. So then if I add those two up, what I'm going to get for my cell potential is a positive value. And that becomes a favorable, spontaneous voltaic cell. So that's what we're looking for. The potential difference of the two electrodes is going to provide a force. So what that positive value means is that there's now a force to push these electrons through a circuit. And this is called the electromotive force, or the voltage. I'm going to stop